Hi everyone, welcome to another episode of Scientific Modeling with Blase. Now, I'm trying to pump out probably a video a day, but I'll probably fall behind. I didn't post really this past weekend, but I got one up yesterday. I'm getting one up today, and I'm just trying to keep the ball rolling so that we can move through and get to some more advanced modeling. I'm still feeling like we have to lay down a little bit of foundation in order for us to get there. And so today we're going to talk about autoregulation. And so autoregulation specifically in E. coli. So autoregulation is just the regulation of oneself, or in the case of genes, a gene's self-regulation. Today I'll really talk about negative autoregulation, but you can have positive autoregulation. Negative autoregulation being that, whatever output protein X, let's say, of a certain gene, X would block the transcription or translation of some sort of itself. So that with a lot of X, you would actually have less gene expression of X. It's kind of a control mechanism. Now you can have positive autoregulation. X can, say, enhance its own regulation. But today we're just going to talk about negative autoregulation. So network motifs. So it's not immediately clear, actually, that autoregulations are a network motif. And so I want to prove it to you that it is, and I'll show that it's statistically significant. Now, network motifs are the building block patterns within complex networks. That is, they are why a certain gene gets expressed when under a complex environmental cue. A motif is the part that leads up to the gene's control. Here I'll show you that a negative autoregulation is, in fact, a network motif within a cell, because like I said, it's not immediately clear. So is autoregulation network motif? This will be the question we'll try and answer today. Let's look at the statistical significance of the E. coli regulatory network and compare it to that of a randomized network. Then we will analyze to see if E. coli have significantly more autoregulation networks than a random network. I have some suggested reading in case you're interested. Okay, and so the way we're going to tackle this is we're going to have a number of nodes in our system. We're going to represent that as n. And I'm also going to have a number of arrows. That is the number of, or the node influencing another node. The arrow is going to represent that gene or that protein's that is an expressed influence on another gene. Okay, so that's going to be an arrow. And so if we have an n number of nodes, I'm actually going to make n a list from, actually, yeah, we'll just make 10 nodes, and let's start with 14. And so we'll come back to this point. I do want to, we actually have to make our function. And so what this function is going to do is essentially arrow pick randomly for each node, or for a random set of nodes within our number of nodes. And so let's actually get into it. And we're actually going to take this and make it the list. So actually we're going to make, the first thing we're going to do within this function is we're going to make n equal the list of range of 0 up to n. But then we're going to make a result. We're going to start with this with empty. Then we're going to have our autoregulation set that we'll append into, and then we're also going to have a counter, because I'm going to use a while loop. So while a is less than or equal to a. Okay, and so in this loop, we're going to append basically the random tuples we create, and if they are the same, if the tuples have equivalent elements, then we'll append them into the autoregulation list. If not, or I guess in both scenarios, we'll still append them to the resulting list. But that's really, the auto list is really what we're going to care about. So let's get n being the random choice. I misspelled that. Oh, I guess I'm not familiar with the way things paste here yet. Random choice, except we're going to store that as a underscore. And then we're going to make our result in this instance equal to the tuple of a underscore n. And then we need to add our condition. So if a underscore n is equal to n, or a underscore is equal to n, we have autoregulation. So we want to actually we want to auto.append our res underscore. And we could go a plus 1. And really the only thing we care about is our length of our list auto, because that's just going to count how many auto-regulation events happen within our regulatory network. And so I could add res, so I'll just go hash, but I don't really care about it. Yeah, so that's that. All right, so I'm going to copy our function from up here. We defined n and a, and we're going to run it down here. Okay, we get 2 lengths of auto, which auto is our auto-regulation list. And so we have 2 auto-regulation lists within this 1014 first go round. If we run it again, 3, 0, 1, 0, 0, 2, 1, okay, 5. Okay, so we see that we have kind of a conceptual understanding of where this might be in terms of range, or where the mean of this, but let's actually find the mean really quick. It'll take just a couple lines of code. So actually what I just did is I just implemented a number of runs functions. So I wanted to run through this arrow picking, let's say 100 times like I defined down here. And so basically we're just going to find a bunch of different lengths of the auto-regulation, that is the number of times an auto-regulation event occurred through our 100 runs. And then we're just going to take the mean of it, and now we're going to output that. And so instead of writing more code where I looped a bunch down here, I'm just going to make that into my definition. And because I imported mean from statistics, this will just be the mean of this length or this list, and the list being just the lengths of our auto-regulation events through our 100 runs, since we defined down here. And so when I run this, I get, of course, a different answer each time because they're just random choices. But 1.5, 1.48, something around there. Great. So now that's going to be really close to actually the way that we can calculate it without just finding the means in this way. And so actually if we just put a over n, that should give us about that as well. So that'll be 1.4. So that's pretty good. That's our actual mean. Now that's just per reference, but I'll stick with this up here because that'll be our most useful thing when we do a t-test below, or most useful element when we do a t-test below. Now when we actually compare this to an E. coli cell, let's actually get our A's and our N's right. So in an E. coli cell, we work with knowing about 519 arrows per 424 nodes. And so we can go ahead and run this randomly real quick. And so if I have 424 nodes, 519 arrows, and I want the mean 100 times, we get 1.16. Right? It's really unlikely that our one node is going to pick itself because there are 424 other nodes. Okay. But in an E. coli, we actually have 40 auto-regulation arrows that we know of. In E. coli. And so that looks pretty significant. Now we're just going to go ahead and prove it by just putting it into a quick t-test to show its significance. And so we're going to import scipy. And then we'll just do scipy.stats.t-test independent. And so actually what we want here is just going to be our lengths of autos that we calculated over the, say, 100 times. And so I'm just going to go ahead and delete this mean. And so we should just get a list of our lengths of autoregulation through our 100 times we defined here. And so it looks like a bunch of 1s, 2s, maybe a 3. Okay, great. And since I know there's 40 auto arrows in E. coli, I'm just going to go ahead and make a list of 40 100 times. Okay, so that should work. I just made a quick list of E. coli. I'm going to append 40 to it 40 times or 100 times. Oh, whoops, this should be 100. We can just make that equal to 100, which is the same amount as right here, which is going to be our length of this list. So I'll go ahead and do that. Whoops. Okay, great. And so now we're going to run E. coli against our length of lists, which we stored as mean. That actually should just work. SciPy has no attribute stats. Maybe I should go from SciPy, import stats. Okay, that worked. That's not probably completely the right way to do it. But anyway, we see that our p-value is extremely low, and thus, it is pretty unlikely that, that this E. coli, it is actually statistically significant that this E. coli have a significantly more autoregulation networks than just a random network that we were to just make via these pseudo-random numbers with Python. So that should do it for this video. This shows you that this is a significant network motif and is clearly used in the E. coli cell. From here, I hope to go into more network motifs, and then I'll actually get into some modeling with it all. But I think this is really important to understand as we move into more complicated networks.